Um, Ethan, have you taken the mid-semester test? I think so. Yes. Okay. So tomorrow is the SPS. I was going to make sure. Yeah, you already took the test. Thank you. Morning, Jack. We wait for a couple of minutes, and then we have more students in class to start the lecture today. Thank you.
Unmarked attendance this morning, and I am disappointed that we never get this done to none. I do not understand why it is so hard to mark the attendance completely by COB each Friday. Every Monday that I sent the report to you, I have asked that the marked attendance needs to be done by COB each Friday. In the regards, Asad in the I received the unmarked. Please let me know what is your plan. Please let in the attached file. Only Jack White's attendance is due to being moved to the new group, and is understandable if it is not done on time. Although it is the convener, a teacher's responsibility to update Jack's attendance, even though you need to mark him from the beginning. Please let me know what is your plan to avoid this. For now, the unmarked attendance as indicated in the attached file needs your attention urgently. Regards.
All right, let's get this started. This is week 9 now, and we have a very important topic in front of us. Given a structure, you want to find out the internal loads. So you remember from last week lectures, uh, once you identify a structure as a beam, there are three types of internal loads you want to describe. So these internal forces are, so this is internal loading, and the structure type we are looking at are beams. Beams are resisting deformation by the action of the bending, and there are three types of internal loads. So these are internal loadings in beams. They are either N of X, that is the axial, and then you have V of X, that is the shearing. So both first one, second one, the unit is Newton, and the third one is the bending moment, M of X, and that the unit is Newton meter. So this week we want to find the relationship between all these. Is there a relationship between N of X, V of X, M of X? Yes, there is a relationship, but the relationship is between the distributed load, W of X. And W of X is how the force is distributed, and the unit for that is Newton per meter or Newton per square meter. This is something like a pressure or intensity of the load. So today we are going to find if there is a relationship between W of X and V of X, relationship between V of X and M of X. And the answer is yes. Actually, once you have a beam, all you have to start with is to find out W of X. So once you find W of X, from W of X you can find V of X, and from V of X you can find M of X. So that is, we go through this with examples. Let's get started with this very simple example. So I'm just grabbing a snapshot from this problem, and then let me bring that into annotation page. All right, here we have a beam. Why this is a beam? Because you can visualize under these loads, this is gonna bend. And when it bends, the radius of curvature changes, either in a what we know as positive bending or negative bending. All right. So that is a beam. The first step is to find the reactions. So we found this to be a symmetric structure with a symmetric reactions 2.5, 2.5. And then the loading changes. There are two zones I can define here. The zone number one, or regime number one, that being the X direction, this being W of X, distributed load. In this zone, we have X changing between 0 to 2 meter. And over here, there is no W of X. W of X in this zone is 0. Okay, so because W of X is 0, and we know by the method of equation the relationship between W of X and shear force, we know that dV is equal to d, this is equal to W dx. So in another word, if we take an integral from both sides of the equation, that is dV is equal to integral of W dx, and left hand side, that is V of X minus V of the beginning. So in this case, V of beginning is A, is equal to W of x is 0. So therefore, I can conclude that V of x is equal to V of A. And V of A, that is when V of A is V at x equal to 0, and that is 2.5 kilonewton. So here, the first in the first zone, I can comfortably describe V of x. So in the first zone, that is V of x, and that is equal to 2.5. So it starts with 2.5, and then it doesn't change for the entire zone, that is 2.5. And what about m of x? For the first zone, we want to find m of x. So I know the relationship between m and v. So that is dm is equal to dv, or that is v dx. So if I integrate, that is m of x minus m of a is equal to integral of v of x, that is 2.5 dx. And that is changing between x equal to 0 to x equal to x. So that is m of x. What is m at the beginning? M at the beginning is 0, is equal to 2.5x. And so I can plot this one when x is equal to b, m of b, that is m at x equal to 2, that is equal to 5 kilonewton meter. So that is 5. So linearly it goes from 0 to 5. That is for the first zone. In the second zone, we have to repeat the very same procedure for the second zone. So let me guide you through that. So this is for zone number 1. What about zone number 2? Okay, zone number 2, for the sake of convenience, I would like to bring the coordinate system right at B. So that is x changing between B and C. But then I bring my coordinate system at the point B, and as such, my x is changing again between 0 and 2. So here, I need to identify W of x for here. But before that, we notice that at the very point B, there is a discontinuous force. So that discontinuity, it means my shear force going from 2.5 traveling 5 in the negative direction. So from plus 2.5, it comes to minus 2.5. So that is very critical to understand. That is minus 2.5. All right, so point B, there are 2 point B. One point B is the left side of the B, I call this B minus, and the B right hand side of B, I call this B plus. At B minus, the shear force is equal to 2.5, and at B plus, V of B is equal to minus 2.5. So when I derive the equation here, for the second zone, I need to consider B plus, not B minus. So here, V of B is equal to minus 2.5. And then when you write W of X for the second zone is equal to 0, dV is equal to W dx, and V of X minus V B plus, that is equal to 0. So therefore, V of X for the second zone, that is minus 2.5. So at this stage, we can comfortably plot the variation of V of X. And suddenly here you have a discontinuous 2.5, which brings that one to the 0. Okay, so we finished the shear force diagram. And for the second zone, how do we write the M of X? So that is dm is equal to V dx. So that is M of X minus M of B plus is equal to minus 2.5 X. MB plus, that is equal to 5. If you bring that to the right hand side, the equation for M of X is minus 2.5 X plus 2.5. So if I all right, let's plot this variation. X equal to 0, that is 2, this is 5. Sorry, this is not 2.5, that's 5. X equal to 0, M is 5. X equal to 4, that is M of C, is M as X equal to 2, that is minus 5 plus 5, that is 0. So therefore, the final point, the bending moment, comes from 5 to 0. All right, so we managed to find the internal forces, the variation of internal forces inside the beam. So from this graph, the conclusion is there is a relationship between W of X, V of X, M of X. So V of X is the integral of W of X, and M of X is the integral of V of X. And the next conclusion is the maximum shear force is 2.5 or minus 2.5, and that is everywhere through the beam. And the maximum bending moment is right in the middle, and that is 5 Newton meter. But these two maximums cannot be compared together because one has the unit of Newton, the other one has the unit of Newton meter. So in the upcoming weeks, we find out by introducing a new variable called stress, we can compare which one is more critical. Is this the shear which is more critical to start the initiate the crack, or is this the bending moment? All right, let's get back to the slides. So here we went through the solution for that. let's try something a little bit more complex. And for this case, I am going to solve this one for you. So here we have a cantilever beam, and this cantilever beam has a triangular distributed load, and we want to find its variation of internal loads. Okay, how do we find the internal loads here? Well, first thing first, let's use some labels. I call this point A, this point B, and then this beam, it has only one zone. So in that zone, X is changing between XA and XB, which is X changing between 0 to 9. And for that zone, what we need is expression of W of X. So that is a very critical task. So how do I find W of X? I know that this is linear, and a line can be written as AX plus B. So we want to find A and B for this equation of the line. If I have the equation of the line here, I can simply integrate to find V and then integrate V to find M. So how do I find this? I know by initial condition. When X is equal to 0, W of X is equal to 0. So that is A times 0 plus B. And from here, I find out that B is equal to 0. But when X is equal to 9, A times 9 plus B, which is 0, that is equal to, this is not equal to 6, that is equal to minus 6. So this is a point where many students don't realize, because this load is pushing down, that is negative. If that was pushing up, like when you have a boat on water, so the buoyance force is a distributed force from bottom to top, that is positive. But here this 6 should be considered as minus 6. So therefore what you get is A is equal to minus 6 over 9, or this is minus 2/3. So here I just simplify that. So anything else I'm gonna erase, just make some room. Okay, now the challenge was to find W of X. The next should be simple, because I know that dV is equal to W of X dx. Okay, so let's find out how this can be expanded. To expand this, you get V of X minus V of A is equal to minus 2/3 X dx, and x is changing between 0 to x. So I know that v of a, that is equal to 9. So therefore, I can write this one v of x minus 9 is equal to the integral of minus 2/3 x, that is minus 2 over 6x squared. All right, so that is equal to minus 1/3 x squared. And therefore you get v of x is equal to minus x squared by 3 plus 9. So we can test this one. When x is equal to 0, v of x is 9. And when you plug x equal to 9, so that is v of b, that is v of 9, that is minus 9 times 9 divided by 3 plus 9. 1, 3, so that is minus 29, which is minus 18, right? So that makes sense, because this is the variation of v of x. So it starts at 9, and from 9 it goes to minus 18. And then because this is negative, that is like so. This is 9. So we have to find an x star. So x star is when shear force becomes 0. So how do I know that? So let me set v of x equal to 0. V of x star is 0. That is minus x star squared by 3 plus 9 equal to 0. That is x star squared is equal to 9 times 3. So x star is root of 3 root 3. So that, if you find out, it's going to be 5.2. So 5.2 meter is very important, because that is where your shear force becomes 0. And then due to the relationship between the shear force being of integral relationship, when shear force is 0, the bending moment is maximum. And we can investigate that easily. So I can write this down as m dm is v dx. So m of x minus m of a is integral of v of x. So v of x, we had v of x here. So let's take this integral. That is so this integral is equal to x cubed 9 plus 9x. So if you plug x equal to 0, that is 0. And if you plug x equal to 9, so m of b, that is m at x equal to 9, that is equal to minus 9 cubed divided by 9 plus 9 times 9. So that is not 9 squared. This is 9 squared. So that is equal to 0. All right. So from 0 to 0, but then in between there is a maximum bending moment. The maximum takes place at x equal to 5.2. So m max, that is m at x equal to 5.2 is equal to minus 5.2 cubed divided by 9 plus 9 times 5.2. And that is equal to 31.2. And the unit is Newton meter. So if I want to plot that, is quite simple. This is a cubic. Yes, let me zoom into everything. Can you see that, Jack? Is this visible now? All right. So that is, you want to plot. Yeah. All right. So let's plot m of x. Starting from 0, ending to 0, and right in the middle, you have the maximum. This is a cubic function, and that's 31.2 Newton meter. So in summary, this was a beam with a distributed load. The first thing was to find an expression for the distributed load. And we know that this distributed load is an equation of a line. Equation of line, you have to calibrate, you have to find the coefficient. So we found this equation of line to be of the shape W of x equal to ax plus b. And then we knew that W of 0 is 0, W of 9 is minus 6. So plugging these two numbers here, we found out the coefficient to be minus 2/3 and 0. So that was plus 0. And then we started from integrating W of x, finding V of x, and integrating V of x, finding M of x. All right. I leave the screen in case if you want to take a snapshot, but you have the solutions also in the slide. The slide give you the. So next example we have is if you have W from W slope point by point, you can construct V, and point by point slope, you can construct M. So that is the relationship. So here, the correct one is, these are the relationships. And so, in another word, you start with W of x, and then integration give you V of x. And okay, let me fix that for you. Sorry for that, Ethan. Thanks for letting me know. Let me fix it for you. If I go to the modules, that is week 9. Yeah, you're right. This is not published. Now it's published. Try it now. You should be able to access it. Thank you, Ethan. Thanks a lot. All right. So these are the important points. When you want to plot shear force, when you want to plot bending moment, the first step is to find the reactions. The second step is to find out how many zones are there. The third step is to find an expression for W of x distributed load. And from distributed load, you start integrating zone by zone to find V of x, and then integrating V of x to find M of x. So let's practice this in some example cases. So that was the first example we did together. And well, let's try this one. Example 11-10. So let's solve this one together. Okay. So just to save your time, I assume that everyone knows how to find the reactions for that beam, so the reactions, and I bring that into a new page. Okay, so this is the problem we want to plot the internal forces, the variation of internal forces. Okay, first thing is making sure we have labels. So I'm labeling the left-hand side as A and the right-hand side label that as B. So, okay, how many zones? Only one zone, zone number one, because the external forces do not change beyond that zone. And this is X between 0 to, and is there a mention of the length? So the length, the total length is 2 meter. The total length is 2 meter. Okay, first thing first, I need to write an expression for W. So who can tell me what is the W of X? W of X is constant, but that constant is negative because it's pushing down. That is minus 500 Newton meter. That's a key step. If you can't identify W correctly, you won't be able to find V of X correctly. You won't be able to find M of X. So it's a very fundamental step to find W of X correctly. So in this case, that is a constant. In the previous case, that was a linear. In the one before that, W of X was 0. So here, the non-zero is a constant, it's a negative. So how do we go from here? Well, we know that dv is equal to w of x dx. So let's solve this equation. If I integrate from both sides between x and a, so that is v of x minus v of a. And by the way, here I know that v of a is equal to 1000 Newton. And I know that m of a is what? M of a is 1000 Newton meter. And is this positive or negative? That's negative, right? According to the convention we introduced last week, this is negative. All right, so let's integrate both sides of here. If I integrate dv, that's v of x minus v of a is equal to minus 5,500 x. And if I plug v of a here, my expression of v of x is minus 500x plus 1000. So we can test this. At x equal to 0, v is plus 1000, and v of b, that is v at x equal to 2, is minus 500 times 2 plus 1000, that is equal to 0. So far so good. We easily can plot the variation of v. So starting at 1000 here, and it's an equation of a line with a negative slope, and it goes to 0 here. So between them the variation is linear, so from 1000 to 0, and that being a positive shear. The maximum shear is at point A. So what about m? So that is dm equal to v dx, and therefore m of x minus m of a. is equal to integral of Vx. So Vx is this one. What is this integral? That is minus 250 x squared plus 1000. Yeah, that is minus. Sorry, this is minus. All right, so let's uh, simplify that. M of x is minus 250 x squared plus 1000 x, and then minus minus plus, that is minus 1000. So that is M of b is equal to m at x equal to 2. All right, so that is minus 1000 plus 2000 minus 1000, that is equal to 0. So therefore the bending moment starts at minus 1000 and goes to 0. So starting at minus 1000 here and going to 0, and then this is a quadratic equation, and the negative is the coefficient of x squared, and therefore this is going to be like a reverse curve. So that is the apex of the quadratic. It's the quadratic, and 1 0. Okay, let me zoom out so you have access to the entire screen. So if you want to take a snapshot, you can. And any questions? Is this clear? You want me to explain any part of this? Okay, any question, please? All right, so no question. Let's go back to the next problem. So that is the detailed solution. And now these are, okay. The next topic we want to cover today, that is the moment of area. Moment of area is a section property, and sections properties are very important because when we discuss the deformation inside the beam structures, we discussed about the internal forces, but internal forces are not the only parameter. The parameters for the performance of a beam, how the performance is affected. So this is controlled by several things. The first one is internal forces. So we know how to find out the internal forces. The second parameter is geometrical parameters. And the third one is the material. All right, so all these factors are critical. It is not only the internal force which can let the beam to fail or crack, grow a crack. The second factor is the geometry. The geometry example of the geometry is the COG, that's the center of gravity. The example is the cross-sectional area, and also that is the centroid of the section. Also, that is the second moment of inertia. So these are all geometrical things: center of gravity, area, um, X bar, Y bar, and I. So because these are dictating the behavior of a structure and they are very important, we want to emphasize on finding the second moment of inertia, or I. I know that you learned about I in energy and motion, and we want to emphasize. And I assure you that in the final exam, there would be questions regarding calculation of A, calculation of X bar, calculation of the area, and center of area. So, second moment of area, we call this I. That is very important. And mathematically, this is defined whether that is about the x-axis or y-axis. That is proportional to the square distance from the neutral plane or the reference datum multiplied by the area. So that integral is called the second moment of area. And it's very uncommon that you have to do this from the mathematical relationship. In real case problems, you only construct or you calculate that using the tables, you calculate that using the primitive shapes. So we start the definition of the second moment of area by introducing some primitive shapes like rectangle, like circle, triangle, and then we go through the compound shape. Compound shapes are the combination of few primitive shapes. For example, if I want to analyze an I shape, right? So I shape is a very common section for a beam. So these can be resolved into one rectangle is a primitive plus another rectangle here and plus another rectangle here, right? So I decompose a complex shape into the primitive shapes. So for every shape, we have their I. This is I1, this is I2, this is I3. And you know what? I is not a vector. I is a scalar. So to find the second moment of area for a composite shape, what we do is we add all the primitive um, components together. Because this is a scalar, you can add them. If that was a vector, you couldn't add them. But the good news is this is a scalar, so you can add them. Let's start with the centroid with a moment of area. And then when we say moment of area doesn't mean anything. Moment of area, second moment of area, has to be defined with respect to a coordinate axis. I mean, you can calculate I with respect to the x, or you can calculate I with respect to the x prime. X prime is passing through the bottom, x is passing through the center. So which one you are looking for? So this one is I bar through the x. You could have calculated this one with respect to the another axis parallel to that. And that brings us to the interesting concepts of, this is called the parallel axis theorem. So with the parallel axis theorem, if I provide you with the second moment of inertia of one axis, you can add a penalty term to find second moment of inertia with another axis, which is parallel to that, and that has a distance of d. So generally speaking, I x prime, that is equal to I x bar plus a penalty term. The penalty term is the distance between the two parallel axes squared multiplied by the area. So area is that area. All right. So this is called the parallel axis theorem. So when you are referring to the table, either the table provides you, the table generally speaking give you that compared to the x bar. And if you need that to any other axis rather than the x bar, you have to calculate the penalty and add this to the standard. So this is the standard, what you find as a table, and that's the penalty. So if you are looking for a standard, you don't have to pay any penalty. If you want to change it with the parallel axis, you have to calculate the penalty and add it to the standard term. Any question? All right, so if we start from scratch, if you start from first principle, the first principle is you want to find Ixx, that is standard value. So you take a typical strip, this typical strip, um, that is the incremental formula. So all you have to do, you have to carry out this integral. So the distance of this strip from the coordinate axis is y. You have to square it and multiply by the area of this strip. And what is this area? The area is, the width is dy and the length is 2x, right? Length of this one is b. So that is equal to y squared multiplied by dA. dA is b times dy. Okay, and that integral is equal to what? That integral is y cubed over 3 b, and what is the variation of y? Y is changing between minus b by 2 to plus b by 2. And if you simplify that integral, by simplification, you can find an equation for that. And then the equation for that is b d cubed over 12. So the standard second moment of inertia is 1 over 12. B is parallel to the x-axis, and d cubed, d is parallel to the y-axis. That is one standard term. You find it in the formula sheet. And in the exam, if you calculating it for the very same shape, well, this is the formula. If you find it with the same shape, a different coordinate axis, you have to calculate the penalty according to the parallel theorem and add it to this one. Or if you are dealing with a composite shape, so you have to break that into a number of primitive shapes, and for each primitive shape, you do the table standard penalty calculation and eventually put all these ingredients together to find the total moment of inertia. Let's do the same thing for a triangle. For a triangle, if I start from the first principle, so that is my coordinate system. So standard means my coordinate system are passing through the CG. And if this is the CG, the height is h, the CG is located h3 and 2h3 on the height, and b by 3, 2b by 3 on the horizontal side. So that is where my coordinate system, the standard coordinate system is. And right, in order to start from the first principle to do the integration, I need an expression of this line. So how do I find the expression of this line? That is the equation of the line. So you know that from the calculus how to derive this line equation. So that is equation of this line. And then next step is to write the first principle equation. Ixx is y squared dA. So I need to take a tiny strip. So this is my tiny strip for calculating the integral. So the area of this tiny strip is dA. That is dy multiplied by x plus, and this is x, right? So you just plug the terms here and then simplify the integral, and eventually you end up with a simple equation. So for the triangle is a primitive shape, so this is second primitive shape. The first primitive shape was a rectangle, the second was a triangle. With a triangle, a standard triangle is when the coordinate axes are at this centroid. Moment of inertia is 1 over 36 bh cubed. So this is very similar. In case of the rectangle, you have 1 over 12 bh cubed. In this case, you have 1 over 36. Okay, so this is 1/3 of that. So don't need to memorize that. In the exam, you will be provided with the formula sheet, or you have access to the formula sheet. But just remember that this is a standard primitive shape. Let's do the same thing for a circle. With a circle, all you need is the equation of the periphery. And then when you make a strip, so this strip is dy, and that is 2x, right? So this is 2x. And how do I find x? This is x in terms of y. So we just simply plug all these special case into the formula. And then after carrying out the integration and simplification, what you find is the standard moment of inertia. This is the third primitive shape. Third primitive shape. For the full circle, the second moment of inertia is pi over 64 multiplied by the diameter to the power of 4. That is the full circle. What if I have a half circle, or what if I have a quarter of the circle? Well, don't worry. The formula sheet give you all the pre-calculated values, the standard ones. So the only manipulation you have to do is, if you want this in a non-standard form, you have to calculate the penalty using the parallel axis theorem and modify the standard term. Where do you get the standard term? You get them from the formula sheet, from the table. So next is the formula for half circle, a quarter circle. And what if I change the x and y? So if I want Ixx, Iyy, simply in this case, they're identical. They're only function of the radius. And that's because of the certain shape of a circle, half circle, or a quarter circle. Okay, no need to memorize this. These are available as a formula sheet during the exam. All you need to remember is the parallel access theorem. So these are the standard values. Calculations are based on the centroid of the shape. But if your coordinate system has an offset with the centroid x and y, so the distance between those offsets will tell you how much penalty you should calculate. And that penalty added to the standard value gives you the current value. So this is a summary of the parallel access theorem. So here you have the current moment of inertia. You break that into a number of, this is a compound shape, So that is, you sum up the individual i's, but then each I would have its own coordinate system. So for every term that you calculate, there is a penalty to calculate. The penalty is the offset between the current coordinate system and the primitive shape coordinate system squared multiplied by the area. That's the penalty. Add the penalty from what you find from the table. That's the standard one. The standard plus the penalty, and add all the terms together. That give you the total moment of inertia, either with respect to the y or with respect to the x. So we could try some exercise, and that is a good exercise. All right, I want everyone to spend um, 15 minutes. So in 15 minutes, we get this problem solved together. So please grab a piece of paper and try to break this shape. This is a compound shape. Try to bring that into number of shape, for example, 1, 2, 3, and do the calculation for each and add the values together. In 15 minutes, we solve this together. Thank you. 15 minutes. Okay, so before getting into the solution for this problem, let me take a attendance. Okay, so we want to find the second moment of inertia for a composite shape. So the rule is the composite shape has to be broken into a number of primitive shapes. But then the key is each individual primitive has its own standard value, has its own coordinate system. So does this composite shape has its own coordinate system? The answer is yes. The composite shape coordinate system should be located at its centroid. So the first step for finding the second moment of inertia of a composite shape or compound shape is to find its centroid. So how do I find the centroid of this one? That is quite simple. So y bar is what we need to find. So I'm breaking that into three shapes. So for each shape, I have to find y hat bar 1 multiplied by area 1 plus y hat bar 2 multiplied by area 2 plus y hat bar 3 multiplied by area 3 and divided by a1 plus a2 plus a3. So the question is, I do need to take a reference. So this x is my datum. So when I find y bar would be calculated with respect to that datum. I could have taken the datum at the top at any place, but now I take that from below. When I calculate, I note that this is my reference. So let's find out what is the centroid of the first shape with respect to this datum. So if that is 20, the y hat bar 1, that is 10, right? So what about the y hat bar of the second shape? The second shape is 160 on top of 20. So 160, the middle of 160, that is 80. 80 plus 200, that makes this 80 plus 20, that is 100. And what about y hat 3? Y hat 3 is 20, 160, 180. And just right in the middle of that is 10. So 180 plus 10 is 190. 190. And I'm sure everyone knows how to calculate the area of each. So A1 is 20 multiplied by 70. Area of 2 is 160 multiplied by 20. And the area of the 3 is 150 multiplied by 20. So if you plug all these values here and do the calculation, you end up with y hat for the compound shape or for the composite shape 118.95. This is a very fundamental step. You have to take this fundamental step to do the calculation. All right, so now we did that. The second step is we just find three I values because this shape, like I said, that is we can decompose that into three shapes. So let me demonstrate that to you. All right, so how do we proceed with this problem? Let me make a quick um, illustration here. All right, so far we know that for the entire shape has its own coordinate system, which is y bar from here. But then that is equal to um, the lower shape plus middle shape plus the top shape, right? So each of these systems, they have their own coordinate system. So this is for the standard, that is the coordinate system for the standard. This is the coordinate system for the standard. This is the coordinate system, right? So for the first one, how much penalty should I pay? I extend this one, and that dimension is how much penalty. So this is, I call this D1. For the second shape, how much penalty should I pay? I extend that line here, and that is how much penalty I pay, D2. And for the third one, that is D3. That is how much penalty I pay, right? So let's bring that shape somewhere in the corner, and then we try to work out the penalties all together. So I'm grabbing all the dimensions from here. Let's find out D1. D1 is the distance between that center line and here. So I only have to subtract 10 mil from that. So D1 is equal to 108.95. Anyone having difficulties digesting that? So what about D2? D2 is from this center. So this center is measured. D2 is 20 plus 80, which is 100. So 100 compared to that, D2 is equal to 18.95. Is that clear? Everyone can follow this. And what about D3? D3 is from here to here. So the total length is how much? The total length is 20, 20, 40, 200 is the total. So that location is 190. So this is 190. So 190 take away from 11895. that is equal to 71. So this is 71. So to calculate the penalty is di squared ai. So the penalty for the first term is d1, which is that squared multiplied by the area of the one. Area of one is what? This is 20 multiplied by 70. What is the penalty for the second term? The second term is d squared, d2 squared multiplied by the area. The area of this one is 20 multiplied by 180. And the penalty for the term is d3 squared, 71 squared multiplied by the area, which is 150 multiplied by 20. All right, so now I demonstrated how the individual components are calculated. So let's get back to the solution we had. So it should be now very easy to understand. So that is the formula. We start with the area of 1. This is the area of 1, highlighted in yellow. So what is the standard value? This is the standard value. You get them from the table. That is 1 over 12 BH3. B is 70 and H is 20 cube. And then the penalty is the area, which is 20 times 70. And that is the offset. Do you remember the offset we calculated for the first shape? The offset for the first shape, or that was 109.95. So that is squared, d1 is squared. That's for the first shape. So let's check this out. Yeah, that is exactly what we had in mind. So this is only the moment of the contribution of second moment of inertia from the lower block, and then we have to do the same thing for the middle block and for the top block. So let's do that for area, the middle block, or area 2. So that just let's set this aside. We try to remember that. And for the middle part, again, the very same formula. From the table, what I get is 1 over 12, that's the standard value. BH3, B is 20, and H is 160 cube. What about the penalty? The penalty is multiplied by the area times D2 squared. The area is 20 times 160. And what about D squared? D squared for the second shape, that was 18.95. 18.95. So let us work this out. Yep, that's exactly the same thing. And then we do that for the third shape. For the third shape, highlighted in yellow, that is the standard shape is 1 over 12 BH3. B is 150 and H is 20 cube. And then plus the penalty. The penalty is the area, 20 times 150. And what was D3? D3, we calculated D3 as 71. 71 is squared. And that should give you the third contribution. Now you have 3 contributions. What you do is you add them, that of the first one plus that of the second one plus that of the third one, and that is the total moment of area for the entire shape. So how are we justified to add them? Because second moment of area is a scalar value. Scalars can be added together like numbers. They are not vectors. So that is why we can add them all together. Okay, so we have one more example here. Can I get everyone grabbing a piece of paper? and try to spend some 15 minutes. So I give you 15 minutes to work this out, and after 15 minutes, we try to solve that together. Your 15 minutes start now. Okay, so let's get this one done. That is a simple problem because when you look at the shape, fortunately there are two primitive shapes. One is the rectangle and the second one is the circle. And then given the symmetry of the shape, the overall thing is has a coordinate system coincide with the primitive shape. So for the primitive shape, the overall coordinate system is like so. And when you break that into pieces, each individual piece has the same coordinate system of the standard. So both circle and the rectangle have the same thing, except the only point here is you have to take away that of the circle from the rectangle. So this is a Boolean operation. We don't add circle to the rectangle because here the material is being removed. So you take this one away from that of the rectangle. But for this one, the I is 1 over 12 BH3, which is 100 times 150 cubed, and no penalty because the distance between the centroid of this one and centroid of the overall shape or compound shape are the same. And for this one, this is minus. For the circle, you remember that was 1 over, I just, yeah, that of the circle from the standard table. Let me just have a look. What was it? Yeah, that of the circle is 1 over 4 pi r squared. So that is pi over 4 radius to the power of 4. That is 25 to the power of 4. Okay, so that is the overall I for the shape. All right, so today what we did in summary, we went through deriving the internal forces in different beam examples. And we did that through correlating W of x distributed load, shearing force V of x, and bending moment M of x. So we solved a number of examples for that. And then we started performance analysis. We know that a beam performance is not only dictated by the internal load, but also with some geometrical terms like centroid, second moment of inertia. Second moment of inertia, we introduced the primitive calculations for primitive shapes like rectangle, triangle, circle. And then we went into the compound shape, how this can be broken into primitive shapes. And then if the primitive value, a standard value from the table is different with that of the compound shape, you have to calculate a penalty. And to calculate the penalty, you go through the parallel axis theorem. And we did some example of that. Okay. Is there any question regarding today or the past lectures? I'm happy to take your questions now. All right, no question. Thanks everyone. Looking forward to see you soon. Take care and I'll talk to you soon. Bye.